Okay, so you probably, if you've been checking the timetable of our progress, you probably realize we're a little bit behind schedule. The final hour was to have been finishing off the multivariate story in the sense of bringing together the dynamics of yesterday, time series, with the multivariate distributions of this morning by having some multivariate time series. And in fact, I will take half an hour to do some of that. It'll be a little bit abbreviated. Copulas is so fundamental that we will be spending more time on it. On Thursday morning, we come back to copulas and dependence, and we recap some of these concepts, and we explore the world of dependent risks in more detail. But we have the elements now to talk a little bit about multivariate time series. We have the idea of arch and gauge. So on this computer here, I brought up arch. So you remember this idea that there is a volatility, and this volatility depends on things in the past. You have arch, you have, if you prefer, gauge, which has a more complicated form here. So on the one hand, we have this, and then I will bring up something. I'll switch over the view in a second when I have what I want to show you. Some of the things that Paul talked about this morning. Paul talked about this one here. Now let's see, we have so many pointers, it must be that one. We have this idea here, which was how you take, in this case, univariate normals and you make them multivariate normal. And then we went on, we made mixed normal distributions by multiplying through by a common scalar variable. So basically, I want to take the idea behind formula 16 and the idea behind this formula here. Maybe not so clever to change the displays like that, but I want to blend these two ideas. So I want to have a model which is multivariate, so it has some explicit dependence on the past, but I want to do it for a vector-valued process. So that's where multivariate gauge comes in. Now I'm confused. I'm going to go back to this projector here. So for the last time. Let's make sure it's completely happy. And we're going to go on to the case of we're going to go on to multivariate gauge. Actually, at this point, 386. Let's go all the way down. So this is chapter 14. So we're no longer following the strict sequence. What did you tell me it was, Frank? 386. There is a quicker trick, go to, but sometimes one just persists with yeah. So we go into multivariate time series. Now, I won't go through everything here. It's included, there's enough here that it tells a coherent story. So what is interesting simply is that it's the same as the univariate story, all the same building blocks, but just for vectors. So it starts with the story of the moments of a time series. It goes on to the idea of stationary. What does it mean to say a vector-valued time series is stationary? Again, you can have strict stationary, you can have covariant stationary. And once you have established or defined a stationary process, you can begin to look at the autocorrelation function, although in this case it's called the correlation matrix function. It's a matrix-valued thing in this case because we have not only correlations within time for different lags, but we have correlations across components. So we get something which is matrix-valued. Now, I'm not going to go into that. I'm just going to point to this and say that we have something very similar, and I'm going to go straight to the multivariate gauge process. Straight to the multivariate gauge process, just dwelling on one definition on the way. We have ideas of noise in multivariate processes. We have the idea of a multivariate white noise, but what you'll need for the definitions is, what is multivariate strict white noise? Well, that is really simple. Xt is a multivariate strict white noise if it's a series of independent, identically distributed random vectors. So it's just the same definition, but for vector objects instead of, or vector valued random variables instead of scalar. So that's about as much as we need to go straight into multivariate gauge processes, and the idea is to just show a couple of definitions and then to estimate them from data and get a feeling for what is possible. So this looks like gauge. So I'm going to say, what's a multivariate gauge process? You build it from strict white noise, but you're going to need something d-dimensional. By the way, we might have reduced dimension first. So we might have gone from 10,000 down to 3 or 7 or something. So let's say d is more modest, but it is bigger than 1. And so what we want to do is we want to create a process out of strict white noise by multiplying by a matrix, and this matrix will depend on the past values of the process. So it will depend on this sigma algebra here, which is constructed from the history of the process up to time t minus 1. Now, how exactly is it going to depend on the past? Well, that is the art of building the multivariate gauge model. There are all kinds of ways we can do it, and in econometrics many papers were produced with specifications that were more and more fancy and had more and more parameters and were more and more difficult to estimate. But I think really there's only 1 or 2 models that are feasible in dimensions higher than 2 or 3, and those are the ones I'm going to focus on. So when you have a model of this kind, I don't have a mean term here. Zt is strict white noise centered at 0. So Zt has some distribution. It could be multivariate normal. It could be multivariate student. In the same way yesterday we had normal distributions, we had student t distributions. It would be something like that. The way it's set up, the expected value of xt given the past of the process is 0, but just as we had for the multivariate normal distribution, you get the covariance matrix of xt, given the past, by taking at times itself, and this is what we call the conditional covariance matrix. So we have a model where there is a conditional covariance matrix, and what we have to do is we have to describe how this conditional covariance matrix depends on the past, and I will use 2 specifications. A few notes. We could add in a conditional mean term. If you remember yesterday, we had armor gauge. We had gauge for the conditional variance. We had armor for the conditional mean. So you could do the same. So, well, here's 2 options. This could be a constant conditional mean, or there are vector armor processes or varmar processes. There's a simple one, which is sort of the analog of AR. That's a vector autoregression of order 1 when you do that. So you could do this, but I won't. For my examples, I will have a 0 mean term. And I will concentrate on modeling AT, this matrix AT, or actually effectively modeling sigma t. There is a very neat decomposition of a covariance matrix in terms of a sandwich here, delta t, pt, delta t. These are 3 matrices. So you maybe have to think about this. The delta t is a diagonal matrix containing the volatilities, the conditional standard deviations. So it's d by d, and on the diagonal it has the conditional standard deviations. Pt has the conditional correlations. Yp, incidentally, capital Latin P is a capital Greek rho, and rho is the favorite letter for correlation. So that's a big rho, T, the conditional correlation matrix, and then the matrix with the conditional standard deviations. So the whole art or science of building a multivariate gauge is to say exactly how these elements depend on the past. How does delta t depend on the past? How does pt depend on the past? And moreover, you've got to do it in a sensible way so that these conditional covariance matrices always remain proper covariance matrices. You heard from Paul that they have to be symmetric and positive semi-definite. Well, let's actually make them positive definite so we don't run into problems of invertibility. So we need this to be guaranteed. For the innovations, the Z's, once again, normal or student, or indeed, as Marius has introduced them, anything spherical would do. In fact, any distribution with mean zero and covariance matrix, the identity would do in here. And I'm going to use another library by Alexios Galanos. And of course, Alexios has put in one or two options for the multivariate innovations as well. So the first possibility that I will look at is the CCC. This was suggested by Engel. Stands for Constant Conditional Correlation gauge. So we have a process of multivariate gauge form where the conditional covariance matrix depends on the past, but this sandwich is simplified. The sandwich, we have delta t, but the pt will be held constant. So pt will be a single constant correlation matrix, positive definite. Del t is diagonal, it contains the volatility, and the elements will follow ordinary gauge. So you have the gauge equation that we revisited, and that's what we're going to do for each component series. Alternatives are, of course, possible. You can put in here any of the univariate gauge specifications. You can have the ones with the asymmetric dynamics according to whether you have a fall or a rise in the variable you're modeling. So anything can go in here. Now, in this process, if you take the matrix of volatilities, this diagonal matrix of volatilities, if you take its inverse and you multiply it by x, and you multiply xt by the inverse, we will call that yt. And this has the effect, this operation has the effect of removing volatility. So doing this to xt in this model will remove volatility, and we will get yt, which I will call the devolatilized process, and this will follow strict white noise, but with a covariance matrix equal to this correlation matrix. So that's sort of easy to check mathematically from the definition that yt, these are in fact independent vectors with correlation matrix PC. So this gives a clue about estimation. This fact here gives a clue about estimation. What if we take each series one at a time, estimate a gauge like this, and then after we've estimated the gauge, that's equivalent to estimating the delta matrix, we then perform this operation, we devolatize, and we get yt, and then to yt, from yt we can just estimate the correlation. So that's what I'm saying here. Estimation can be accomplished in two stages. Fit univariate gauge models to each component series, form some residuals, some devolatilized data. Of course, whether it really is devolatilized or not depends on the quality of the gauge model you've chosen, or the quality of the fit of the gauge models you've chosen. But gauge 1.1 will probably do a reasonable job, and then all you have to do is estimate this correlation matrix. So that's easy to do, and the alternative is to do a big maximization of everything in one step, which is a little more challenging. This model is very much the starting point, and from which to proceed to more complex models. And I think it's generally agreed by people who've fitted this model to data that it's not good enough in most cases. In some settings it might give an adequate performance, but it's generally considered that the constant conditional correlation is unrealistic, and that not only should the impact of news be felt on the volatilities, the standard deviations, but it should also affect the dynamic evolution of correlation, or of conditional correlation. So CCC is not really used so much. Instead, the model which is used and the one which I will fit is DCC, Dynamic Conditional Correlation. Once again, I'm reciting ideas of Engel here. And so we'll fit this one with the RM Gauge package. So go back to 76. What has changed? Everything is really as in 76. Except that the PC, we no longer have a constant PC, we have a PT. And we have to decide how PT depends on the past. And the way we do it is through this strange equation here, 77. So we have 3 bits. This is something analogous to first order Gauge, but for the correlation matrix. So there is a constant term, there is a PC, there's a constant term, and then we add on combinations of the devolatilized process times itself at lag values. In effect, we are going to choose P equals Q equals 1. So just think of one lag value, and we will also take one lag value of PT. So we'll take PT minus 1. But by the time I add this, and this, and this, what I have in brackets here is probably not a correlation matrix. So I have this funny thing here, because when I add these 3 things up, I get something which isn't a correlation matrix. It will be positive definite, that's okay, but it will be a covariance matrix. And so I have to do this little operation that takes a covariance matrix and changes it into a correlation matrix.
So, question from a notation, those alpha and betas have nothing to do with the alpha and betas for the Gauge?
Yeah, they have nothing to do with the alphas and betas from the Gauge. It's perhaps unfortunate that these are not the alphas and betas from the Gauge. These are some new alphas and betas specifically for the correlation matrices. So I think everything here we've talked about. This is a constant correlation matrix. If you like, this is the long-run correlation matrix. Rho is an operator that just gets correlation matrices from covariance matrices. YT is the devolatilized process, so dividing through by the standard deviations. And actually, it's going to be the case that these alphas have to sum to something less than 1 to get a model that doesn't explode and makes some kind of sense. Now here...
And again, it's guaranteed that these Y's are white noise, strict white noise.
No. They needn't be strict white. In this model, they're probably not going to be strict white noise. There's going to be some dependencies in them. They are just devolatilized, but they're not independent in this model. In the previous model, they were in the CCC. It's a little bit tricky. So CCC is a special case when those alphas and betas are 0. By analogy with the univariate Gauge model, you can sort of see what happens. In a univariate Gauge, in fact, you have an updating equation of this form. The volatility equation can be written like this, that sigma t squared is given by the unconditional variance. You have that, there should be a square there. There should be a square there, obviously. So a term involving squares of x, t, and previous variances. So this is for Gauge itself. So if we compare that one and that one, you get an idea of what is happening. So you can think of, thus, in DCC, this PC, you can think of it as representing the long-run correlation structure. So how do you estimate it? Or how do most people estimate it? And how does Alexios Galanos estimate it in his R code? Well, you fit univariate Gauge models to each series. That gives you an estimate of delta t. You devolatize, you get yt hat. You estimate the long-run correlation structure by applying some correlation estimator to the yt hats. And then finally, in the third step, you estimate the parameters governing the dynamics of correlation. And so, because when you see these multi-step methods, you ask, does this give good estimates? Does it give consistent estimates? Does it give efficient estimates? And in the econometrics papers, they've been through the asymptotics and decided that is the case. We will we will just fit the first order model. We'll fit the first order model, P equals Q equals 1. We'll do it by, well, the final stage, stage 3, will be done by a maximum likelihood method, or a conditional maximum likelihood method. I think this slide is not worth going through. Instead, what I want to do is fit it and then come back to a few points. Okay, so this will be chapter 14, if anyone's looking for it. There is but one script in chapter 14, MGOJ. MGOJ estimation. We need XTS, we need some data, any data you want, but I take QRM data, and we need RM GOJ as opposed to RU GOJ. And I will celebrate the UK and Switzerland by taking the FTSE and the SMI. So I'll do a bivariate example. So so I have these two indexes, a bivariate example. I mean, it's just, obviously it's a simplistic example just to show what happens in these models. I want log returns. As usual, I get the log returns. I see lots of nice volatility clustering, so I know that GOJ is going to be important here. And I take 4 years of data. That's the pairwise scatter plot, incidentally. And I've got 1,000 data going into this estimation, 1,000 bivariate data. Now, what do I have to do to fit a DCC model? Well, I have to specify the univariate models I'm going to use. And I can take any of the univariate things in the RU GOJ package, but I will take standard GOJ of order 1, 1. Actually, I've thrown in a mean model. I've thrown in an AR mean model, an autoregressive mean model, and an unconditional mean term. But that's not too important. And for estimating the parameters of the marginal model, I will use student innovations in the likelihood. So this is what I call USPEC, USPEC for univariate specification. And I'll just quickly define it. Now for later purposes, and we won't look at them until later, for later purposes, I have fitted a marginal model using the UGOJ fit to the first component, the FTSE returns, and I've fitted a marginal model to the second component, the SMI returns. And I'll just keep those results back, and then we'll look at them later. For the DCC, I need a multivariate specification. So the syntax is a little bit complicated. After having done a univariate spec, I make a multi-spec. I make a multi-spec, which is I basically just collect together my univariate specifications for each of the components. And as I've said, it needn't have been the same specification. I could have had 2 different specifications. I could have worked on these series individually and had different specifications. But I put them together in a multi-spec, and then finally, I spec my DCC model. I make a specification for the DCC model, and that consists of my marginal specification made in multi-spec, the order of the DCC, 1, 1, and then the choice of distribution, which you cannot quite see, but it will say MVT. So we take multivariate student. And this is, by the time I get here, I've spec'd my DCC model. So there's a few stages to it. Then I'm ready to fit it. So then I fit it, and the cursor disappears for a few seconds, and then it comes back, and in mod, I have the results. And once again, there's quite a lot of output, but here's the things, well, actually there's not so much as in the univariate, but here's the DCC GOJ fit. The distribution is multivariate student. The model is DCC of order 1, 1. There are 16 parameters in here, 2 series, and you get some information about the log likelihood, but you'll see the parameters now emerging, that for the FTSE, there are all the parameters that specify the model, the Gauch model for the FTSE. And I did put in some autoregression, but that's not so important. You see the parameters of the Gauch. And then there are the parameters for the SMI. And then here are the two parameters for the dynamics of correlation. Okay, these are the ones for the dynamics of correlation. And finally, this is the degree of freedom. It's not that small, actually. The degree of freedom 9 for the multivariate student. You can, the reason I fitted the other models earlier is you can now sort of compare, you can just see that basically what's happened is that the univariate model has been fitted and these parameters are exactly the same as what are ultimately emitted for FTSE, and these are the parameters that are estimated for SMI. So literally what has happened is the univariate ones have been fitted first, and then in 2 subsequent stages all the other parameters have been determined. Well, whether you call that 2 stages or 3 stages depends on what you put in each stage. I put here a 2-stage fit. First univariate gauge, standardized residuals are extracted. That is the process of devolatilization. Then a model with dynamically changing conditional correlation is fitted. It's done in stages, but ideally it would be nicer to estimate everything in one global optimization. But the way that RM Gauch works, it's done in stages, and perhaps for clarity about what's happening, that is not so bad. What comes out of here? Okay, so that's the blue line here is the estimated volatility. Blue line is the estimated volatility for FTSE. Here's the financial crisis. Here's the blue line estimated volatility for SMI returns. So we have the volatilities. That's the conditional covariance. Conditional covariance here. Look at this spike in covariance in 2008. But what about conditional correlation? What does that look like? That looks like that. Now, conditional correlation, for a start, the axes run from 0.5 to 0.9. So everything is positive here, the correlations. And it oscillates around. What exactly does it do in the financial crisis? Well, the financial crisis is somewhere up here. Okay, pretty high correlations. The financial crisis was a long thing, but Lehman Brothers. So the demise of Lehman Brothers is what? September 2008. September. I want to say it's about here. Yeah, might have to look a bit more carefully, but it's moving around, this conditional correlation. So when people look at this, when people look at the covariances, of course, you have to remember that a large part of that comes from the volatility explosion, but there could also be a higher conditional correlation there in that period. So well, maybe we can map it. I have grid lines in my plot which aren't quite visible on the screen, which allow me to say that, yeah, in fact, this is exactly where Lehman Brothers was, right up there. And there's some other plots which I won't go into. Okay. Now, you could fit a CCC model and formally test, do we need dynamics for correlation, or could we take the conditional correlation constant? You would overwhelmingly conclude that, in fact, it does add something to have dynamics of correlation. To finish with, there is a relationship here to copulas. So we've got far enough into copulas to know that there is a Gauss copula and a T copula. And these models we fitted are, in fact, examples of dynamic copula models, because what we have is what I called the devolatilized process. Well, let's take two cases. In fact, the one that I fitted has a student innovation distribution. If I'd chosen a Gaussian innovation distribution, I would have a model where the devolatilized process, conditional on the past, effectively has a Gauss copula with normal margins and a correlation matrix PT, which is evolving dynamically according to that equation that you saw. So this notation here means a Gauss copula, standard normal margins, and a correlation that's evolving according to that updating equation. The one I fitted was this one, where I have a T copula. The degree of freedom doesn't change. That is held constant. But the correlation matrix is updating according to those equations. The marginals match the copula. The degree of freedom is the same. Now, a very natural question is, can I have a model where the degrees of freedom of the margins do not match the degree of freedom of the copula? And you can. And that is called copula M-Gauch. And Alexios has put that into his package as well. So for those of you who like that kind of thing, there is further down, and I'm not going to do it, C-Gauch spec, which stands for copula Gauch spec. And this is a model where the degrees of freedom of the margins are allowed to differ from the degree of freedom of the copula. So you get an even richer dynamic copula model. No, they can differ. You can have one margin with 6, another with 7, or 9, and the copula itself can be 5, that kind of thing. So, but that's a whole another story. But just to tell you what's out there, and it's probably advanced enough to go for a general audience, but I hope at least you get a sense of what's possible. And we're sort of ending on time, and if anyone's interested in that, do ask. M for multivariate.